All right, we're going to talk about scatterplots, correlation, and regression. This is just an introduction to it. We are going to delve deeper into it later on. Okay, so a scatterplot and correlation. So a correlation exists between two variables when the values of one variable show associated with the values of another variable. Linear correlation exists between two variables when there's a correlation and the plotted points of paired data result in a pattern that can be approximated by a straight line. So if I have linear regression, the points are going to look like a straight line. A scatter plot or a scatter diagram is a plot of paired XY coordinates, quantitative data with a horizontal x-axis and a vertical y-axis. The horizontal axis is used for the first variable x, and the vertical axis is used for the second variable y. You guys have done a lot of scatter plots before. We've done quite a few of them. So here's an example of different types of correlation. So here we have a positive correlation, right? All these numbers look like they're in a line here. They're very close together. We're traveling up towards the right, so we would call that a positive correlation. So here our data values are traveling from left to right down. So we would call that a negative correlation. And then we have no correlation. So here we have these data values, and it almost looks like you could just put a line in any direction and kind of split that data up, and it's going to be there. So this would be no correlation. So here we have some clusters and gaps. Now, this is, if you remember back when we talked about the different weights on pennies, this is some stuff that could happen in a scatter plot. You might have clusters of them, and then a gap, and then more clusters. And so what this is signifying here is, like in those pennies, we had that gap of weights. Okay, so these are pennies in year prior to 83 or whatever, and these are pennies after. Okay, so linear correlation. So when we're looking at the linear correlation coefficient is denoted by R. And it measures the strength of the linear association between two variables. So in your book, they gave you an example of 5 data points, and it was shoe print length to height. So what I did here is I created a scatter plot here with shoe print length and height here. And then what I did is I took that information, so I took this data here, and I plugged it into regression statistics. I used Excel, but there's a lot of other ones you can get. And so when we look at this, we want to look right here at our what we call multiple R, R value. The nice thing when you're using a computer program is there's a lot more information than just this that it gave me. And so, but I just pulled this. So here we have our multiple R of 0.591269. So this is our linear coefficient, okay? So we're going to talk about, so remember this value of 0.591. We're going to talk about how that, makes this look. So if we look at our data, does this look like a line would represent that data? So correlation or no correlation. So remember that value of 0.591. So if the computed linear correlation coefficient R lies in the left or right tail, there is sufficient evidence to support the claim of linear correlation. If not, there is not enough evidence to support it. So here is our number of pairs of data. So how much data do we have? The less amount of data we have, the higher our critical value has to be. Okay? So here, in our last one, we had 5 data points. So we have to get within 0.878. So if we look here, this is kind of what they're talking about. So they create a number line from -1 to 1, okay? And then they're going to plot this critical value of 0.878. If I fall between these two values here, in here, there is no correlation. I have to fall in this little tail right here, okay? So if we remember back our sample data from the previous page, we see that our data value of 0.591. So 0.591 might be about here, okay? And since this falls between -8.87 and 8.78, there is not enough information to determine a linear correlation. We just don't know. Okay, so it might have a linear correlation. We need more data. We just don't know if it does yet. Okay, p-value. So if there really is no linear correlation between two variables, the p-value is the probability of getting paired sample data with a linear correlation coefficient R that is at least as extreme as the one obtained from the paired sample data. Okay, so what we want is we want a p-value that is very, very small. If we have a p-value that is very small, the likelihood is that there is a linear correlation. So only a small p-value such as 0.05 or less, so we're talking about a 5% chance or less, suggests that the sample results are not likely to occur by chance when there is no linear correlation. So small p-value supports a conclusion that there is a linear correlation between the two variables. Okay, so we want small values for p to indicate that there is a correlation. We want large values for R to show that there is. Okay, so regression. Given a collection of paired sample data, the regression line or line of best fit or least squares line, because this is talking about the distance from point to line, is the straight line that best fits the scatter plot of the data. The specific criterion for the best fitting straight line is the least squares property described in section 10.2. We'll get to that later. Okay, so this is the equation here for a regression line. A lot of you are going to look at that and go, well, I know that. That's very similar to y equals mx plus b. That's true, it is. But we want to use this idea because we want to find b sub 0 and b sub 1 using some kind of statistical software. Okay, b sub 0 is the y-intercept and b sub 1 is the slope. So this is just an example of regression line. Here's our data. They plug this into a computer program, got this line here, and kind of developed from there. So that's our kind of talking about a real introduction to scatter plots, correlation, and regression.